Section 15.4 in Stewart's textbook, which is 15.6 in Thomas's textbook. It's about center of mass and inertia of a lamina. So the definition of center of mass, basically in layman's term, is the balance point of an object. So when you find the center of mass of an object, you're trying to find the balance point of an object. In other words, if you have an object, where would you put your finger on that object to balance it up? So if you have point masses, which are like isolate masses on the x-axis, let's say you got mass 1, mass 2, and 3, which they happen to be what? Positioned at x1, x2, x3, and so on and so forth. The center of mass of these point masses is defined, which is denoted by x bar, which is a weighted average. It's the mass of each object times the distance from a reference point divided by the total mass. So in this case is m3 times x3, m2 times x2, m1 times x1 divided by m1 plus m2 plus x3, m3. So this is like a weighted average. That's why we use a bar on top of the x, which stands for the center of mass of these three masses, which they happen to be x1, x2, and x3 many units away from a reference point. That point happens to be center of mass, which is also known as a balance point. Problem is, what? Is the sum of the masses times the difference of these distances from the balance point always adds up to 0. That indicates there is no tendency for what? This supposedly this is a lever to rotate. So that's why it comes up always 0, rain or shine. However, the problem is, what do we do when we have a continuous mass density? In other words, what if the density of these masses is a function of x along the lever, and in terms of the units, let's say it's going to be so many grams per second, centimeters. So the analogous for this formula would be something like this. So the center of mass, if the what? Density is continuous, so you know it's not discrete like this guy. So what happens is, instead of, let's say, what? You have point masses along the x-axis. What if you have a region like along the x and y axis? And now what? Or what if, as I said, the density is continuous? It's a function of x. In that case, you take the what? Antiderivative of the density times the distance divided by what? Antiderivative of density dx. In turns, the numerator stands for something called moment, okay, which is mass times distance, and the denominator is what we know as mass. So if you happen to be on in R2, that means you are what? In x and y plane, and here is your region R. Then the center of mass is defined as x bar equals moment about the y-axis over m, and y bar is equal to moment about the x-axis over m. In other words, the center of mass is an ordered pair now. It's not just a single number, because you're dealing with a region in xy plane. And turns out the moment about the y-axis is density times distance. So, mass times distance. Which distance? The distance from the center of mass of what? Of the object to the what? Y-axis, which happens to be x. And the moment about the x-axis is mass times the distance from the center of the object, center of mass of the object to the x-axis, which is y. So these are the distances. If you take these distances away, so you just what? Perform the double integral of density times area, that's mass, which happens to show up in what? The denominators of both fractions. So once again, the numerator in for x bar represents what? Moment about the y-axis. Denominator is the mass. Numerator for y bar is moment about the x-axis divided by mass. I will explain that a little bit in more details in the next page or the next 2 pages. However, the question is, what if you are dealing with a solid? Okay, how would you find this balance point of a solid? In this case, instead of taking the moment about the x or y axis, you have to take the moment about the yz plane, moment about the xc plane, and moment about the xy plane, and divide it by the mass of the object. However, the mass, now it's defined as what? Triple integral density, okay, times unit volume. Do you see it? Whereas before it was density times unit area. Notice we had dA, but now for solids it's triple integral density times unit what? Volume. So now the center of mass, okay, for what? For solid is defined as x bar equals moment about the yz plane over m, and y bar is moment about the xc plane over m, and z bar is moment about the xy plane over m. So you will have a triple order of numbers. Do you all see it? So basically, we have a lamina. So let's concentrate on what? Two-dimensional objects, which are known as lamina. Lamina is like a flat region on what? X and Y plane. There are some well-known laminas which you can just by inspection and common sense find the center of mass. For instance, the center of mass of a rectangle is where the diagonals intersect. The center of mass of a triangle is where the median, the point where the median of the triangle is. Square is the same as rectangle. Circle is at the center. But the question is, what if you have an irregular shape like this guy? How would you find the center of mass? Well, first of all, mass has 3 definitions depending on the type of objects you're dealing with. Mass could be area times density for laminas. That means if you are in R2, right? Mass could be length times density if you are dealing with one-dimensional objects like a thin wire or a coat hanger. Mass is also defined as volume times density for solids. That's like if you are in R3. So notice the definition of mass varies depending on the nature of the object. But now what's a moment? Moment is denoted by capital M, is the amount of force which produces rotation about a specific point or axis. And it's defined as mass times perpendicular distance from the center of mass to that axis. So therefore, for two-dimensional objects like lamina, we have 2 moments, one about the x-axis, one about the y-axis. And as you remember, the definition of center of mass for laminas is what? Is moment about the, for x bar is moment about the y-axis divided by mass. And for y bar is what? Moment about the x-axis divided by mass. Examples of moment could be the moment of force, which you know it from previous chapters. It's called torque, correct? And we could also have angular momentum, and that would be like rotational moment. That's like when the motion is what? Circular motion. So with that said, how would you find the center of mass of a rectangular region if the mass density is a function of xy? In other words, rho or delta. Remember, we showed the density either using the what? Greek letter delta or rho. So this also could show up as delta, a function of xy, is e to the xy. So in other words, when the density is not constant, so that means the material the object is made is not the same throughout the region. You know, portion of the, let's say, object is made of wood, portion of it is made of metal. So the density is a function of what? The position, the point you select on the object. It's not constant. However, if the density is uniform, that means what? You have a constant density. So the terminology, instead of saying center of mass, we refer to those kind of regions as what? The balance point of those regions or solid as centroid. So centroid refers to center of mass of what? Regions or solids where the density is constant. That means the entire solid or entire region is made of same material. So to find a mass, you remember the definition was for two-dimensional objects, density times area. So here's the density, here's the area. I use double integral, but I have a rectangular region, so that means what? The limits are constant. So if I go, let's say, dy dx, so I'm going from 0 to 1, 0 to 1. That should be pretty easy integral. So there you have it. That's the answer. Now I have to find two moments, moment about the y-axis, moment about the x-axis. What do I do now? You copy the what? Double integral for mass exactly just the way it is over here, right? But you multiply the mass by distance from the center of mass to the what? This is like about the y-axis to the y-axis. So in other words, if this is my rectangular region, you know, 0, 1, 0, 1, and this is like what? The y-axis. Here's the center of mass. For moment about the y-axis, I multiply the mass by what? This distance. I'm going to call it x. That's what x is for. And moment about the x-axis is the what? Distance from the center of mass, you know, perpendicular distance from the center of mass to the x-axis, and I'm going to call that y, and that's what this y is for. So as you can tell, when you're finding the moments, you just copy the what? The double integral with the same limits, same integrands, except you would add x for moment about the y-axis, and you would add what? Y factor for what? When you're computing moment about the x-axis. So when you find these three quantities, these guys, you know, the mass and the moments, now you are ready to find the center of mass of that particular region. So remember how this comes about. This is x bar is equal to moment about the y-axis over mass, and this is y bar, which is moment about the x-axis over mass, and that's called center of mass. Sometimes, due to the nature of the what region or solid, you can tell by common sense where the center of mass should be located. You don't really um, have to know calculus in order to tell where exactly the center of mass is. For instance, the center of mass of this hemisphere has to be somewhere what? Along the z-axis due to the symmetry, correct? So when it comes to finding the center of mass, you know for sure x bar and y bar due to the symmetry is 0. So all you have to do, find the z component of the center of mass, and that would really cut down the work into 1/3. Do you see it? So take advantage of the symmetry when you're finding the what? Center of mass for a region or a solid. It doesn't really matter. So So basically, these are the formulas for laminas. So mass is what? Density times unit area. Moment about the x-axis is exactly the same formula, except I have a y here. Moment about the y-axis is exactly the same as mass, which I have, but the difference is I have an x component. Here's the question. Suppose you have this region which is trapped between x plus 2 and x squared. So here's x squared, and this is the line y equals x plus 2. I'd like to find the center of mass, which is the balance point of this region, if the density is what? Is a function of x. So this is given. This region is given. I'd like to find the center of mass. Common sense tells me the center of mass has to be somewhere around here, so I can put my finger there and maintain this region in balance. So what you do, you use the double integral. So because this is lamina, so the definition is density, which is given to us as k squared. Incidentally, in this case, k is constant, times the unit area, which I took at dy dx. And I took my element vertically, so I'm going from parabola to the line. And for x, limits for x, I have to find the point of intersections of the line and the what? Parabola, which happens to be -1 to, what is this? 2. -1 to 2. So you go from curve to curve, point to point. Anyways, so when you do it, you get 63 over 20k. Now it's time to find the moments, the amount of force which would resist what? This region to rotate about the axis or about the what? Y-axis, x-axis or y-axis. Those are called moments. As a matter of fact, they're called first moments. All you do is what? Copy exactly the mass over, except now you have to what? Remember the definition of moment is mass times distance. So for moment about the x-axis, multiply the integrand by y. Moment about the y-axis, multiply the integrand by x. Keep the same limit, same setup, but now you have extra factors in your integrands. So take those under consideration and come up with appropriate answers, such as these guys. So now you take the ratio of this moment about the y-axis over mass, and that's what this is, and then the ratio of this moment about the x-axis over mass, form the ratio, simplify. Excuse me, at the end of the day, you get center of mass is equal to 8 over 7, comma 118 over 49, which is about 1.14, comma 2.4. And that's about right. Remember, our first initial guess was this, and the mathematics confirms our initial guess, which the center of mass has to be around here. It can't be way up here or way down here. It has to be somewhere in the center, no? And that's basically how you find center of mass. Well, then we have something called moment of inertia, which is denoted by capital I. Moment of inertia is what? Defined as mass times density times distance squared. So remember, this is sometimes called second moment in physics classes. So moment was dense mass times density. Moment of inertia is mass times density squared. And where does that come from? As I said, it comes straight from physics classes, because if an object is in motion, the kinetic energy is defined as half of what? Mass times velocity squared, okay? But when you have a rotation, linear velocity is what? Related to angular velocity with this formula. V is equal to R times, this is called omega, which is the same as angular velocity, correct? This is linear velocity, this is angular velocity. This has to do with what? Arc length, because you are in a what? Circular motion. This has to do with theta, how fast the theta is changing, how fast the arc length is changing. So this is omega, which is angular velocity, and it's related to linear velocity this way. What that means in kinetic energy, if I go and replace the V with what? R times omega, I get half of what? Mass R squared omega squared. M times R squared by physicists is defined as moment of what? Inertia. Basically, moment of inertia measures the rotational inertia of a body. Okay, it tells you how hard it is to rotate an object about an axis or a point of reference. So therefore, we have three moment of inertias. Moment of inertia about the x-axis, which is what? Mass times distance squared. This much is mass. This much is distance squared. About the y-axis, this is mass. This is distance squared. And about the origin, you just add these guys up, which is what? Double integral mass times x squared plus y squared gives you what? The moment about the what? In a moment of inertia about the what? Origin. So moment of inertia is used to calculate angular momentum and allows us to explain how rotational motion changes when the distribution of the mass changes. What would be example of moment of inertia? It would be like rotational shaft, okay? And the shaft's moment of inertia is analogous to object's mass. What I'm saying is, think of picture your car. What makes the car, start and stop is the mass. What makes the wheels of the car, the tires to rotate, start or stop, has to do with what? Moment of inertia. In other words, moment of inertia, which is also called what? Second moment. It has to do with how hard it is for an object to rotate. Another example of it is a flywheel, which is a typical it's a device in the engine of your car. The crank, the so-called the crankshaft. So flywheel is used to maintain a constant angular velocity of the crankshaft in a reciprocating what? Engine. So flywheel is mounted on the crankshaft, stores energy when the torque is what? Exerted on it by a firing pistons, and it releases energy to its mechanical loads when no piston is exerting torque on it. So that was basically the definition of a flywheel in the engine, on the engine of a car. So finally, let's do a center of mass of a solid. Okay, here's the solid. The solid is bounded by this cylindrical surface and this plane and these planes. And the constant and the density is constant. So what we are talking about, we're talking about something called centroid. So instead of saying find the center of mass, the statement of the problem will show up, find the centroid of the solid. Why? Because the density is constant. As I said, either you use the delta or you use the rho. Either Greek letters are used in what? In physics or mathematics. So this is how the solid looks like. In order to find mass, remember for solids, mass is what? Density times volume, and moment is mass times density, distance. But when you're talking about solids, this distance could be from the center of mass, in this case centroid, about xy plane, xz plane, about xy plane, about what? YZ plane. So it's not about axis, it's about those three planes in three-dimensional coordinate system. So in this case, I shine the light, I'm viewing this object this way from the front. So X goes first, and my projection is going to be on the what? YZ plane. So right about here, right there. So that would be like the shadow of what? My object, my solid on the YZ plane. On the YZ plane, if I graph this on the YZ plane, it's a parabola going upside down. It hits the y-axis at -1 and 1 and the z-axis at 1. So that's the region. That's the shadow. So what you do, you kind of go, okay, x goes from back, which is front, all the way to the front, okay, but the front is the plane. The top is the what? Cylindrical surface. The back end, what? The back is the coordinate system because it says so, but the front is not what? The cylindrical surface. The front is the plane. And you just notice how flat this is. But the top is the what? Is so the sides are the planes, but the top of the solid is that cylindrical surface. So anyways, you go from what? You solve this for z, so that would be for x, that will be 1 minus z. And now you get your what? YZ limits from the projection of the solid onto what? YZ plane, which is a parabola. So what I did, I took my element vertically, okay? So z goes from the y-axis to the curve, which is 1 minus y squared. And as you can tell from the diagram, y goes from -1 to 1. So it's very crucial to have the solid and its projection in front of you so you can set up the limits. Unfortunately, there are no magic formulas to set these limits of triple integrals. So you get an answer. Now copy this mass integral precisely what? Over. But now to find the moment about the what? YZ plane, you have to multiply the mass by x. And that is the distance of the center of mass of this solid to the what? YZ plane. For xz plane, you multiply the integrand by y. For xy plane, you multiply the integrand by z. When you compute these moments, okay, you get these three numbers, okay. And now the definition of center of mass, what for a solid is, for x bar is moment about the yz over mass, y bar moment about the xz over mass, z bar moment about the what? Xy over mass. So take each of these guys and divide it by what? Mass, but follow the order here. And lo and behold, you get 5 over 14, 0, 2 over 7. So this is the center of mass, which is also known as, in this case, centroid, because the density was constant. It was not function of x and y and z. As a matter of fact, I should have had a function of x and y and z because I'm in three-dimensional space. Sorry about that, guys. So this should be rho of x, y, z is equal to 4. And this should be delta of what? Of x, y, z, which is the same as a rho of x, y, z, which is equal to 4, which is constant. Thank you.